Germany's capital, Berlin, has a population of almost 4 million people, with more than 100,000 buildings. Supplying these buildings with climate-neutral heat is a major challenge. The amount of green energy required is enormous. Taco Holthausen is professor at the Berliner Hochschule für Technik and an expert in sustainable building construction. The heat supply for offices and apartments here requires roughly as much energy from renewable sources as the whole state of Brandenburg, which surrounds Berlin, can supply. So we need to make the best possible use of energy within the city. There are a limited number of wind and solar power plants in the countryside surrounding Berlin. They cannot supply such a large city with completely climate-neutral energy. Renewable energy sources therefore need to be within the city as well, and they need to be as efficient as possible. One example is the Dockyard waterfront offices located directly on the Spree River. There's very little space between the main road and the waterfront, but a great deal of energy is necessary for the 30,000 square meters of office space. For the heating alone, the building requires as much energy as roughly 200 newly built one-family houses. Large photovoltaic modules and solar thermal systems have been installed on the roof to supply green energy. Scientists and engineers developed a concept to make optimum use of the environmental energy. Funnily enough, an old railroad tunnel plays an important role. This is where freight trains used to run underground in Berlin, connecting the port to the nearby railroad lines. This is a huge seasonal thermal storage system. We store the heat from the summer for the winter, and then we use it to heat this large office building. Once the construction work is finished, the heat from the building will flow during the summer into the tunnel that has been flooded with water. So-called plate heat exchangers then heat around 1,500 cubic meters of water. We've got a total of 14 plate heat exchanger modules spread over 120 meters. The total area of absorption is over 1,600 square meters. That's like 2.5 soccer fields. A water glycol mixture, known as brine, flows into the plate heat exchangers via a pipe system that is several hundred meters long. Both heat and cold can be stored in the tunnel. The plate heat exchangers are located in the storage tank directly next to the building. Once the construction work is completed, the tunnel will be flooded with water. The water glycol mixture then flows through the inside of the heat exchangers. In the summer, the brine transports heat from the building into the storage tank. The storage tank next to the Spree River was sunk into the groundwater. This tunnel is partially in groundwater, so there are requirements protecting it. It may not be cooled down or warmed up too much, and not above 20 degrees. The storage tank should reach its maximum temperature at the end of the summer. When temperatures drop and heating becomes necessary, the brine will then absorb heat from the storage tank. The brine then flows inside the building to large heat pumps. The heat pumps use this energy. Running on electricity, they bring up the temperature of the water in the storage tank from around 20 degrees Celsius to that of heating water. Radiant ceiling panels in the offices, as well as other heat exchangers, keep the building at a pleasant temperature. Due to the large amount of heat in the storage tank, green electricity can be used very efficiently for heating. At the same time, the water in the storage tank continues to cool down. During the winter, we are constantly extracting heat from the water using a heat pump, which makes it colder and colder. At some point, the temperature is below freezing and ice forms in the heat exchanger plates. Eventually, the whole tunnel is frozen through like a large block of ice. The process is called latent heat utilization. We have a heat extraction rate of 80 to 0 degrees Celsius. The plate heat exchangers extract the last bit of heat from the 0-degree cold water, and it freezes. During this change of state from liquid to solid, the same amount of heat can still be extracted from the water as when the water is being cooled from 80 degrees to 0 degrees Celsius. This physical phenomenon is also put to use here in Berlin. This way, a large amount of additional heat can be extracted from the water. In February, the first ice particles form on the plates. By the end of the winter, 1,500 cubic meters of water have frozen into a large block. The ice can expand without bursting the tank. The formation of ice on the heat exchanger plates is one of the largest blocks of ice in Europe. And a word about us. Renewables.film conveys the energy transition through journalistic films. We would be grateful for your support so that science and technology documentaries of high quality can continue to be produced. You can find more information under the video in the description. The storage tank in the former railroad tunnel makes it possible to store the heat from the summer and use it optimally in the winter. 3 large heat pumps in the basement of the building are vital for the energy management. Together, they have an output of over 1 megawatt. Conventional heat pumps use refrigerants that have a high global warming potential if they are handled improperly and leak. That's why we use heat pumps here that use ammonia, a natural refrigerant. The 3 heat pumps all work according to the same principle. Hot ammonia flows into a special heat exchanger, the so-called condenser. Here the gas transfers heat to a water circuit via a heat exchanger. The water is heated by the hot gas to 65 degrees Celsius. Depending on the requirements of the system, from around 33 degrees to up to 65 degrees Celsius are possible. The ammonia cools down and liquefies. The liquid flows through a valve. Since there is less pressure behind the valve, the ammonia cools down. The cooled liquid ammonia now flows into an evaporator. The mixture of water and glycol, the brine, which comes from the large water storage tank, also flows through this. The brine flows in at a maximum temperature of 25 degrees Celsius and can be cooled down to minus 25 degrees Celsius by the ammonia. The ammonia absorbs heat from the brine and vaporizes. The ammonia gas now flows to an electrically driven compressor. By compressing the gas, the temperature increases once again. The hot gas flows back to the condenser, and the cycle starts all over again. This cools the brine circuit on one side and heats the water circuit on the other, which means that thermal energy is raised to a higher level. Due to the high energy density of the ammonia and the special design, the heat pumps operate with a high thermal output and are very efficient overall. The heat pumps are working all through the winter. The water in the storage tank freezes through before the end of the heating period. In order to have sufficient ambient heat available, technicians install a supplementary energy source on the roof of the building. In addition to a conventional photovoltaic system, they also use a special kind of solar module. Michael Viernickel helped develop the building's complex energy management system. Solar energy provides us with radiation that we can use to create electricity, like in the collectors here on the right. However, we are only able to obtain around 20% of the energy. But there is a large amount of heat that also comes from the sun, and if we want to utilize this heat, we use photovoltaic thermal hybrid solar collectors, or PVT collectors. The PVT modules are a recent innovation, combining solar cells and thermally open solar collectors. When the sun shines, the cells produce solar power, and the entire module heats up. There is also a heat exchanger on the back of the PV cells. The brine flows through this heat exchanger as well. The heat pumps then use this thermal energy to heat the building. But even when the sun is not shining, the collectors can still use renewable energy. The heat exchangers extract heat from the ambient air. The energy that is generated can also be used by the heat pump to heat the building. This means that the PVT system is able to use 3 different green energies: solar power, solar heat, and the renewable energy of the ambient air. The PVT collectors are installed on an area of over 1,700 square meters. In addition, normal photovoltaic modules harvest green electricity here as well. Due to a combination of year-round storage, innovative solar modules, and efficient heat pumps, it is possible over the course of a year to produce 4.5 kilowatt hours of heat from just the 1 kilowatt hour of electricity consumed by the heat pumps. Now that is efficient. However, the system has another challenge to overcome. The effects of climate change will increase in the coming decades. Cities are getting hotter and hotter, especially in the summer. The perceived temperature inside a city can be up to 10 degrees higher than outside the city. And this apparent temperature, what it feels like, will only increase. The dockyard has around 5,000 square meters of glass surfaces. Most of them are facing south. Without air conditioning, the offices would overheat.
We're going
to need more and more energy for cooling and less for heating. Cities are heating up more and more, getting hotter and hotter, and that will become a much, much bigger issue. This is an issue that the coming generations will have to deal with. The engineers have, of course, factored climate change into their energy management and supply the building not only with heat, but also with cooling. In addition to storing ice, they also use the ground beneath the building. To do that, they drill bored piles into the ground. The location of the building next to the river meant that first off it had to be structurally secure. This was done with bored piles. And these bored piles, in turn, can be used to store energy by supplying or removing heat, depending on whether the building needs cooling or heating. It's not difficult. You build something for structural reasons, like these board piles, and then use it to store energy. The cooling energy from the ice is needed for the summer. On the first warm days of the year, the cooling will come out of the ground. Around 100 concrete piles have been bored on one side of the building and on the banks of the river. The pilings are there for stability on the otherwise sandy ground, yet inside these pilings are pipes filled with water. There are also many thin water pipes under the floor slab of the building. Circulation pumps transport the coolness of the underground water into the building. If the water that had been stored below ground is below 15 degrees Celsius, the offices can be cooled directly via the radiant ceiling panels. After a few weeks, the board piles and the ground under the building have warmed up to over 15 degrees. Direct cooling is now no longer possible. The heat pumps therefore cool the board piles and the subsoil again during the night. During this cooling process, the heat pumps produce heat. The heat then flows onto the roof at night, and the modules are heated up. The heat is then released into the Berlin night sky. And all without heating up the city's climate. In contrast to an air conditioning system, we do not create heat in order to cool the air, nor is our system loud. We emit heat into the sky via radiant heat without causing any noise. There is less noise and less strain on the urban climate, which would otherwise continue to be heated up by conventional air conditioning. Conventional air conditioning systems generate a hot stream of air that is blown out of the appliances and heats up the surroundings. With PVT modules, the heat escapes as infrared radiation directly into the night sky. In the dockyards, however, cooling via the board piles and the ground is not enough at the height of summer due to the large glass facade. In very hot weather, cooling therefore comes from the ice storage tank. The cold water initially flows directly back to the radiant ceiling panels. The ice block then begins to thaw. By August at the latest, the ice will have completely melted, and the water in the reservoir will be warmer than 15 degrees Celsius. Now it can no longer be cooled directly either. The heat pumps now produce cold for the building again. The resulting heat then flows into the large water storage tank. However, the water storage tank must not be heated up too much. At night, the heat pumps then cool the storage tank down again. The waste heat that has been collected is released back into the night sky via the heat exchangers of the PVT modules. The large water tank serves as an intermediate storage tank for the heat. By the start of the heating period, the water in the tank will have warmed up to a maximum of 25 degrees Celsius. And the annual heating and cooling cycle starts all over again. Thanks to efficient management of the large water and ice storage tank, it is possible to produce around 7.5 kilowatt hours of cooling from the 1 kilowatt hour of electricity consumed by the heat pumps over the course of the year. This means that not only the heating, but also the cooling of the building is very efficient. A large part of the electricity for the heat pumps comes from the building's own roof. We have a self-learning system to improve efficiency, and AI will help us to optimize these processes. The goal is to use as little power from the grid as possible and to operate the building with our own energy on-site as much as possible. The renewable sources available at the dockyard produce about 90% of the total energy required in the building over the year. All this despite the limited space available in the center of a big city. The use of AI means that renewables and storage systems are used as best as possible. The aim is to ensure that electricity is only drawn when there's a wind and the sun is shining. This also keeps electricity prices low. Climate change poses major challenges for almost all larger cities. In the middle of Berlin, the dockyard on the Spree River not only has an excellent energy balance, but can serve as a bona fide role model.